Good morning to everybody, and thank you for attending this talk. I am Andrea Mauri. I work for 15 years in the Milano Chemometrics and QSR research group, and I co-founded now Alvascience, that is a software company where I am the head of informatics. Alvascience is a software company focused on developing chemoinformatics software tools, specifically software for molecular descriptors calculation, molecular dataset curation, QSAR, QSPR model building, and the novo molecular design software. In this presentation, I will give you an overview of the novo molecular design using machine learning techniques. Specifically, I will present you the usage of genetic algorithms to design new molecules with desired characteristics. The described implementation is available in our tool, alvaBuilder. If you have already seen a presentation or if you have read a paper about the novo molecular design, you will be probably familiar with this slide and these numbers. Anyway, in order to provide you with an idea of the challenges we are facing with when dealing with the novo molecular design, this is an estimation of the dimension of the chemical space. Chemical space is huge, and the number of organic compounds that could be synthesized is enormous. Different values have been proposed during the last years, but generally, the number of synthesizable organic compounds is estimated between 10 to the 30th to 10 to the 60th molecules. To understand how much is huge the chemical space, you can consider that the stars in the Milky Way are approximately 10 to the 11. Even if the chemical space is so big, we already explored only a small part of it. For example, the number of molecules included in the Cas registry number is currently less than 200 millions. And you have also taken into account that the compounds that are included in the Cas registry number are both organic and inorganic substances. Anyway, we have also to keep in mind that the number of drug-like molecules is a tiny fraction of the whole chemical universe. And when we explore the chemical space, we don't want to explore the whole space, but we typically want to identify new drugs or new drug-like molecules. One thing that I like to say is that looking for new molecules using the novo molecular design is something like the exploration of the universe, but having as a goal the finding of only those stars that includes in their solar system potential life-bearing planets. So we are not just exploring the universe or the chemical space, but we are focused on exploring the chemical space in order to find the specific target molecules. Furthermore, we have to also consider that the exploration of the chemical space is getting harder, or at least the identification of new drugs is getting harder during the last decades. And this decreased ability of finding new drugs has been called Irum's law, where the Irum's law is just a Moore's law spelled backwards. What is the Moore's law? The Moore's law is a law that was defined to describe the exponential increase in the number of transistors that can be placed onto an integrated circuit. This number doubled every 2 years since the 1970s, and this term is used more generally for those technologies that improve exponentially over time. And we can see that the drug discovery is not increasing its capability during time, but is decreasing its capability of finding new drugs over time. And since we have seen that the chemical space is so huge and we don't have a map to explore the chemical space, its exploration can be an unfeasible task. Therefore, we need some help. And this help can be provided by machine learning techniques. Machine learning techniques can be used to explore the chemical space in a more optimized way, helping chemists to identify new molecules that are potential new drugs, and we can do that using machine learning techniques in a faster and a cheaper way. So let's have a look on how machine learning techniques, specifically genetic algorithms, have been implemented in alvaBuilder to design new optimized molecules. alvaBuilder is a graphical tool that is designed in order to facilitate the user in the de novo molecular design process. And alvaBuilder uses genetic algorithms as an optimization process that, starting from an initial population and through an iterative process, try to optimize the desired molecule characteristics. alvaBuilder is a graphical tool and is available for Linux, Mac, macOS, and Windows. So, how genetic algorithms can be used in the de novo molecular design process? Genetic algorithm is a machine learning technique that is inspired by Charles Darwin theories of natural evolution. And this type of algorithms reflects the process of natural selection, where the best individuals are selected for reproduction and mutation in order to produce new individuals for the next generation. In our case, the individuals are the molecules, and we will see now how molecules are represented and how reproduction, mutation, and evaluation steps works. The novo molecular generation using alvaBuilder requires that the user perform just two steps: the selection of an initial training dataset containing the reference molecules, and the definition of the target properties that we want the generated molecules to have. Once these steps have been performed, the automatic molecule generation can start. And the main steps of automatic molecule generation are the initialization, that is performed just one time, and then the reproduction, mutation, and evaluation that are performed iteratively for a set of times. And every step, including reproduction, mutation, and evaluation, is called a generation. The initialization step is performed randomly selecting a subset of the molecules included in the training set, and this subset of molecules randomly selected will be the initial genetic algorithm population of molecules. The goal of genetic algorithms is to improve the population through small changes to the best individuals belonging to the population, and these changes are performed via reproduction and mutation step. So let's have a look on how these steps are performed and how molecules are represented in alvaBuilder in order to perform these steps. Using alvaBuilder, all the molecules included in the training set are represented as a combination of fragments. These fragments are those inspired by the Bemis and Murkoff work, where all the molecules are split in three types of fragments. The first type of fragments is the ring systems, that are all the isolated or fused rings. The second type of fragments are the linkers, that are all the substructural features that do not include rings, but are connected to two or more ring systems. And finally, the side chains, that are those substructural features that are connected to just one ring system. In this representation, every piece of puzzle is a molecular fragment, and the combination of different pieces of puzzles connected one to each other is a molecule. So let's have a look on how the reproduction step works. The reproduction steps is performed selecting randomly two individuals, so two molecules from the population. And these two individuals are called parents. And with a crossover operation, two new individuals are designed, the children. The reproduction is performed randomly selecting a pair of molecules, A and B, from the population. Each molecule in the couple is split in two. In this case, molecule A is split in two parts, A1 and A2. Every part can be constituted by one or more fragments. And the second molecule B is split in two parts, B1 and B2. Then a crossover operation is applied to generate two new molecules. The molecules are composed by part A1 and B2, so as part taken from molecule A and a part taken from molecule B. And in the same way, the second child is constituted by the part B1 and the part A2. So it's a combination of the two original parents. And then the two resulting molecules are added to the population. So this is the reproduction step. After the reproduction step, the mutation step is performed, and the mutation step is performed on a percentage of the new population that has been created during the previous step. And for every mutation, a molecule and a fragment is selected. alvaBuilder implements 3 different types of mutation. The first type is performed replacing a terminal fragment, in this case the pink fragment, with a hydrogen atom. So basically, it's in this step, a fragment is eliminated from the molecule. The second type of mutation is performed replacing a hydrogen atom with a fragment taken from the training set. In this case, a hydrogen atom is replaced with the dark green fragment, the dark green piece of puzzle. And then the last type of mutation that is performed replacing a fragment in the molecule with another fragment taken from the training set that is compatible with the original fragment that is removed by the molecule. Then, after reproduction and mutation steps have been performed, all the newly designed molecules will be evaluated. Take into account that after the manipulation of molecules throughout the reproduction and mutation steps, the resulting molecules are still valid molecules, so there are molecules with valid valencies and valid ring systems. During this phase, the evaluation step, the score of all the molecules of the new population is evaluated using the user-defined score function. And the molecules are sorted by score, and only the best molecules are preserved. The score function is defined by the user using a set of rules. And the score function is an aggregation of these of the rules defined by the final user, where each rule can be of 3 different types: a molecular descriptor rule, a similarity-based rule, and a structural features rule. The descriptor rule is used to find molecules that have a target value for a specific descriptor. Target value that we can define that we want to look for molecules that have a lower value for this target value for these molecular descriptors, or we can define also a range of values that we want that the molecules will have. And this is the molecular descriptor rule. Then we have the similarity-based rule, that is a rule that can be used to find molecules that are similar or dissimilar to the target one. The target molecule will be specified by the user. And finally, we have a match rule, a structural feature rule, that can be used to reward those molecules that contain or not a given substructural feature. The score is then aggregated considering all rules, and the aggregation function can be performed using the arithmetic or the geometric mean. The result of a score function is a number between 0, that characterize the worst molecules, and 1, that characterize the best molecules. In addition to the rules that are defined and used for evaluating the molecules, using alvaBuilder, it's also possible to define a fixed structural features that all generated molecules must contain. For example, it is possible to define a specific scaffold or a specific ring system that every molecule that will be generated by alvaBuilder will contain. So let's have a deeper look into the rule based on molecular descriptors. alvaBuilder calculates almost 100 molecular descriptors, including constitutional indices, molecular properties, and drug-like indices. Defining a rule based on molecular descriptors, it's possible to add some boundaries to the chemical space that we want to explore. For example, we can define rules based on molecular size, for example, using the molecular weight, the number of atoms, or the number of rings, and so on. But we can also define boundaries or target values for a specific physicochemical property, like the octanol water partition coefficient, the aqueous solubility, or the topological polar surface area. And finally, we can also define a rule based on descriptors that can help us in the identification of molecules that can be synthesizable or that can be drug-like molecules. This can be done using two specific descriptors. Those descriptors are the synthetic accessibility score and the quantitative estimation of drug likeness. The synthetic accessibility score have been proposed by Hertel and co-author in 2009 in order to evaluate the synthetic accessibility of drug-like molecules. And this score is based on the combination of the fragment score and the complexity score. The fragment score has been defined by analyzing common structural features in a large number of already synthesized molecules, and it is calculated considering the fragments that belongs to a molecule and the frequency of these fragments in already synthesized molecules. In some way, as stated by the authors, it captures the historical synthetic knowledge, and it does it comparing the fragments that are present in already synthesized molecules and their frequencies, the frequencies of these fragments, with the fragments that are included in the molecule under evaluation. Conversely, the complexity score is a number that describes the presence of complex structural features in the molecules, and it is calculation as a combination of information about molecular size, type and size of rings, and stereo information. The values of SAscore are in the range between 1 and 10. Molecules with high SAscore values should be difficult to synthesize, whereas molecules with low SAscore values should be easily synthesizable. So let's have a look on two examples. We can see on the left side a molecule with a low value SAscore, so that is considered easily synthesizable, and the molecule with the highest value of the SAscore, that is a molecule that is considered to be difficult to be synthesized. So let's now have a look on the other descriptor that can be used during the de novo molecular design process. That is the QED, the quantitative estimation of drug likeness, that have been proposed in 2012 by Bickerton and co-authors. And this descriptor has been proposed in order to provide a quantitative estimation of drug likeness of molecules. And it is calculated using 8 molecular properties that are considered relevant in determining the drug likeness, such as the molecular weight, the octanol water partition coefficient, and so on. The QED is based on the concept of desirability, and its values can range from 0, when all properties are unfavorable, to 1, where all properties are favorable. So let's have a look at 2 examples also for this type of descriptors. We have on the left a molecule with a high value of QED. So it's considered a molecule that can be considered a drug likeness molecule, and a molecule with low value of QED, that is a molecule that is on the right side of the slide, that is a molecule that can be considered a not drug-like molecule. The concept of synthetic accessibility and drug likeness plays an important role when selecting compounds during the early stages of drug discovery, and they can help the generative process to exclude those molecules with undesired characteristics at the early stage. So, concluding, machine learning techniques are very promising when dealing with de novo molecular design, since they can help us the exploration of the chemical space, and so they can help researchers to move on a path that optimizes the molecular characteristics. So we have seen that we don't have a map, but machine learning can explore the chemical space in a better way. And so we designed alvaBuilder, that is a easy-to-use software tool provided with a graphical user interface. And we developed alvaBuilder with the goal of developing a tool that requires just few intuitive steps in order to guide the user in the molecular design process. The main advantages of this approach are based on that is based on molecular descriptor, fragments, and genetic algorithms, is that the generated molecules will be unique and valid molecules. And where with valid molecules, we intend those molecules with usual valencies and without the presence of not synthesizable ring systems. So the next steps, we are looking forward and we are evaluating to add into alvaBuilder new rule types. Specifically, we are evaluating to implement a rule based on QSR, QSPR models, enabling alvaBuilder to optimize molecules that have, for example, a specific value for a specific endpoint, for example, low toxicity value or high activities, and so on. So, thank you very much for your attention.